The purpose of this video is to explain the mathematical structure and derive a basic and fundamental version of Einstein's field equation. The Einstein field equation is a story of the geometry of space-time and gravity authored by God through Jesus Christ. Colossians 1 verses 15 through 16 state that the Son is the image of the invisible God, the firstborn over all creation. For in him all living things were created, things in heaven and on earth, visible and invisible, whether thrones or powers or rulers or authorities. All things have been created through him and for him. The prerequisite knowledge required for this video lies in differential geometry and 4 degrees of freedom, i.e. multivariable calculus, matrices in linear algebra, and at least a basic understanding of motion in physics. Although some aspects of the tutorial lie in advanced algebra and calculus, the step-by-step derivation will allow comprehension that surmounts this issue. Moreover, the purpose of this video is to elucidate the mathematical structure of Einstein's field equations and define it and its components. Thence, for the purpose of learning, feel free to rewind the video, pause, and read and take notes. With that being said, the full Einstein field equation can be presented in its basic form such that, as seen here, where this figure denotes the Einstein tensor, this figure the product of the cosmological constant, pronounced lambda, and the metric tensor here, and the stress energy tensor as we see here. What is referred to as the Einstein tensor, right here, has a value such that, as we see here, where this figure denotes the Riemann or Ricci tensor, and R denotes the scalar curvature constant, and once more the metric tensor, as we see here. In this heuristic derivation of the Einstein field equation, we will omit cosmological expansion, this figure here, and give a brief explanation towards the end of the presentation. Hence, we present a rudimentary form of the equation such that, as given here, which subsequently can be expressed as we see here. We begin with the force space coordinates, which are the Minkowski coordinates of ct times x, y, and z, where ct is the temporal coordinate, which is the product of the velocity of light c and time t, and the spatial coordinates x, y, and z. Where function phi is a map from n-dimensional real numbers here to a real number within the set of real numbers here, r, as expressed here, where this is the map phi from n-dimensional real numbers to singular dimension real numbers, which are scalars. The term differential refers to a smooth surface with no asymptotes where the operation of differentiation can occur. Hence, a space-time manifold can be defined as a field function here, defined on the Minkowski coordinates, as we see here. Hence, a space-time manifold can be defined as a field function, as we see here, defined on the Minkowski coordinates of here. Thus, a basic example of a field function, as we see here, is this expression here, where partial derivatives of the field function in respect to the Minkowski coordinates here are given here, where we have each partial derivative in respect to the temporal coordinate and x, y, and z, the spatial coordinates, which gives us the values of each partial derivative. Partial derivatives are important to the derivation and mathematical structure of Einstein's field equations. Thus, the space-time curve and thus the manifold function phi can be described as positive, negative, or flat, as conveyed by the following illustration. Thus, we have positive curvature, which is spherical, and then negative curvature, which has a saddle shape, and then flat curvature or flat space. And here we have the image credit to the original website that produced these images, right here. Moving forward, the four space coordinates of CT, X, Y, and Z will be expressed in this notation, so we see the equivalence. Hence, the partial derivatives on the space-time manifold can be expressed in terms of this notation, such that, hence, the spatial coordinates can be expressed as we see here, or the position value. Therefore, for our example, the field function or manifold function here can be denoted phi expressed such that is expressed such that. In other words, we're re-expressing the original example in terms of the new notation. The partial derivatives in this example have values in terms of coordinate x such that, which are the same values with the new notation again. Okay. The partial derivatives can be denoted by this and can be expressed by the equivalence of here, which is a gradient vector which has an equal expression to, as we see here. So for our example, we have the values of the gradient vector using our example, as we see here. In deriving Einstein's field equations, the space-time metric is an important component of the equation. The space-time metric is a form of the Pythagorean theorem as expressed here. With 4 degrees of freedom, we look at the form of the Pythagorean theorem right here with 4 degrees of freedom. Prior to continuing with this, we introduced the symmetric property. Symmetry is an integral part of Einstein's field equation. The property of symmetry is given by, you see, if x of A equals x of C equals x of B, then x of A equals x of B, which imply that x of A equals x of B equals x of C. Everything equals each other. And again, this is along the same degree of freedom or axis of freedom. A differential element is an infinitesimally small displacement in variable x or position x, which is the limit as the change in x denoted delta x approaches 0, as we'll see shortly. The displacement delta x is expressed as the difference between the final position denoted x final and the initial position or denoted x initial, as shown here. We have the entire equation right here. So now we're going to show the limit. The differential element is denoted this. The differential element is mathematically expressed as shown here, which is a limit, as we were saying, which shows that the change dx becomes infinitesimally small as values of delta x approach 0. In reference to the displacement on our space-time manifold, each differential element dx corresponds to a gradient vector. This correspondence can be expressed mathematically as shown here. Thus, we re-express the gradient vector as the following, where we see each differential element corresponds to an infinitesimal change, which are the partial derivatives. Therefore, in terms of infinitesimal displacement on a field function phi, the displacements can be expressed here, incorporating the field function phi acting on, which means the partial derivative acts on the field function phi, which gives us expression incorporating it. This can alternatively be expressed as right here, as displayed here. Thus, the symmetric expressions of these vectors and symmetric positions along each degree of freedom or axis are given such that, as we see here, hence the vectors have an equivalent expression along each degree of freedom or axis such that, as we see here. Therefore, the product of gradient vectors can be expressed such that, as we see here, for the purpose of a fundamental explanation, consider four vectors A and B expressed as we see here. Thus, here we have the dot product between vectors A and B expressed such that, as we see here. This expression of the dot product can be expressed as the sum of products shown here. Reverting to the expression in terms of differentials, the symmetric property of product differential expressions can be expressed as the equivalence of here. See, the product of these two differentials equal the sigma notation. This expression is in the form of the previously mentioned Pythagorean theorem. Thus, the dot product of partial derivatives, or here, can be expressed as a sum, as we see here. The variable ds is referred to as the space-time interval and has a value, as we see here, which can alternatively be expressed as we see here with sigma notation. Prior to introducing the metric tensor, I would like to introduce tensors and therefore tensor ranks. Number one, a tensor of rank 0 is a scalar or simply a number, example 9. Number two, a tensor of rank 1 is a vector, as we see here. Number three, a tensor of rank 2 is a matrix, as we see here. At this juncture, we introduce the rank 2 4x4 metric tensor, where the subscript A denotes the column position and B denotes the row position. Hence, the 4x4 metric tensor can be expressed as we see here with its components. We relate the components of the metric tensor to the partial derivative on field function phi as shown here. Hence, the components here of the metric tensor are the products of partial derivatives on a field function phi such that, as we see here. At this point, the differential element dx can be expressed as a vector, as shown here. Consider the differential elements dx and d of x of b. The symmetric property again applies as shown here. Hence, the differential elements dx and x can be presented as the column and row vectors as we see here. So we have the column vector and the row vector of differential elements. Thus, the product of elements dx and dx of a and dx of b and the metric tensor can be expressed such that, so we have the products, the multiplication of all three. Multiplying the column vector dx to the metric tensor gives a value such that, and furthermore, multiplying the row vector dx of b in the expression above to the expression means distributing this gives a value as we see here. Thus, in terms of the summation or the sigma sign, the expression can be written such that, in terms of differentials, this can be expressed such that, as we see here. Therefore, the spacetime interval ds can be expressed in terms of the metric tensor such that, okay, where we see that we replace the differentials with the metric tensor, which these are equivalent expressions. Therefore, expressing the spacetime interval ds in terms of differentials gives us, as we see here, a particular scenario is if the spacetime interval ds is composed of components of or its corresponding metric tensor that is a diagonal matrix as shown below. So we have the metric tensor here with where the only non-zero components are in the diagonal and the rest are zero as we see here. If the metric tensor is a diagonal matrix, then the equation of the spacetime interval ds will incorporate the Kronecker delta, which is equal to the piecewise function shown below, which states that the Kronecker delta equals 0 equals 1 if the components a and b are equal. And conversely, the Kronecker delta equals 0 if the components a and b are not equal, as we see here. Thus, The corresponding value of the spacetime interval ds can be expressed such that, incorporating the Kronecker delta, as we see here. Hence, this sum is given such that, we see here, this concludes a complete description of the spacetime metric. Therefore, at this juncture, we can define and derive the geodesic. Geodesics. Movements or displacements along our surface are referred to as geodesics. Geodesics, also referred to as world lines, are the straightest possible curves. The following illustration shows geodesic world lines on curved manifold surfaces. The geodesic is an intricate part of Einstein's field equation. The following illustration demonstrates geodesic lines pictorially. All right, so here we see donut-shaped spacetime manifolds where the red lines are the geodesic lines, so the straightest possible curves along them. And of course, we give credit to the website that produced it right here, where the red lines in the illustration constitute geodesic lines on the donut-shaped curved manifolds. At this juncture, we introduce and begin a heuristic derivation of the geodesic equation. If our field function or manifold function phi was a straight line, then the first derivative of the function would be a zero, as conveyed here, where the position values x are referred to as critical points. Thus, geodesics are the straightest possible curves on a curved linear surface, or simply a curved surface with a linear system embedded on it. Therefore, our first goal in defining a geodesic is to obtain a derivative that gives the straightest possible curve. Thus, in defining a geodesic and obtaining the derivative of the straightest possible curve, we consider the equivalence of expressions of the space-time interval such that, where we see all the equivalent expressions here. However, for our purposes, we use the term here for the space-time interval. Furthermore, we have, therefore, in finding the straightest possible curve on our curved manifold M defined by field function phi, where a linear metric defined by, which is equal to that, we take the first partial derivative of the space-time metric and set it equal to zero, such that, see, we take this derivative, you see this derivative is applied to the space-time metric and set it equal to zero, with the reminder that the partial derivative of the gradient vector is this expression or equation. Therefore, we have this expression. We eliminate the products of differential elements, which are these, which gives us this without the differential elements, as we see here. We just divide it across and they cancel out or vanish. Using the symmetric equivalence principle, we set the initial expression equal to an equivalent expression in terms of A, B, and C, as we see, or they can be referred to as subscripts, A, B, C, and D. See, so indices or the subscripts, same thing, as shown here. Thus, we re-express the derivative expressions with a substitution of the initial derivative such that, here, subtracting the left side or this side of the equation across gives us this expression. Okay, so we subtracted this over to here, which gives this expression. Now consider the notation right here, C of Fi of I of K, which equals the product of differentials. Okay, so this equals this, which is also equal to the derivative acting on the metric tensor. So these are all equivalent expressions right here. where variable CIFK, or I'll just refer to it as a figure, retain the property of symmetry elucidated earlier in the video, as seen here, and of course along the same degree of freedom or access. Thus, the product rule applies to the variable as demonstrated here. So we apply the product rule of calculus here. We substitute the variable here into the previously expressed equation of this. So we're going to substitute into this, which gives us this, or set it equal to it. This gives the expansion of here, when we set these notations equal to this. So you notice that we have this plus this equals this plus this minus this. So this corresponds with this term corresponds with this term, and this term corresponds with this term, all equal to 0. Applying the product rule to the variable gives this, which is just reiterating what these two expressions here, the product rule of that. Substituting this into the expression here, or the left side of the equation, gives, so we applied the product rule to this term here, which gives us this in brackets, which equals this, as we saw earlier. Thus, or this term, I should say, the left side of the equation reduces, as seen here. So these two cancel out, and this plus this, they're all symmetric, so you get 2c here, which equals all of that. Okay, dividing the coefficient 2 to both sides of the equation give this. So we divided the 2 across, and we now obtain that. Recall the expressions of the metric tensor in terms of differentials right here. Substituting the expression of the metric tensor here into the variable c gives, or substituting this into this equation, gives us this equation in terms of the metric tensor as seen here. Once more, the goal is to obtain a derivative of the straightest possible curve. Thus, we multiply variable this by the inverse of the metric tensor. This is the inverse tensor with indices in the superscript. So we see that the indices of the inverse tensor are on the upper side. It's in the superscript. The inverse of the metric tensor, denoted this, is the inverse of the metric tensor, which is with seen here with lower subscripts, with the indices in the subscripts, meaning that the product of these two tensors equal the 4x4 identity matrix, as we see here. Hence, the product of the metric tensor and its inverse, these two, can be expressed as shown here, where we multiply the metric tensor times its inverse tensor, which equals the identity matrix, as we see here. This product, or this, can be expressed as equivalently this. These two expressions are equal, which in terms of the identity matrix is synonymous to 1 in our expressions, as demonstrated here. It's synonymous to 1 only in the expressions. So we have this equals that, as we see there. Therefore, we multiply this variable by the inverse metric tensor. So you see that we multiply this across, the inverse across, I should say. Distributing the inverse metric tensor across the right side of the equation gives, as we see here. Where the expressions are all symmetric, the identity can be substituted into the equation, as we see here. So we see the identity being substituted as a result of multiplying the inverse tensor to the metric tensor up here, and they all disappear and are replaced with the identity matrix, which is equivalent to the expression as we see here. Thus, we have accomplished the goal of reducing the product of this to the partial derivatives which constitute a single composite partial derivative that gives the straightest possible curve on the manifold. Here we introduce the Christoffel symbol, which is set equal to the product here. So we show that here. Thus, the Christoffel symbol can be expressed with the conventional value of here. This is expressed in many textbooks and in general relativity as that, the value of the Christoffel symbol, as we move on to the geodesic equation. Consider the products of differentials previously expressed which equals 0 as shown below. Subtracting the term on the left side of the equation gives, all right, so we subtracted this term to the left side on both sides, which gives this expression, and multiplying the reciprocal of -1 on both sides of the equation gives this expression. So we multiply both sides of this equation by -1, which gives this. Therefore, here, recall the equation that we just derived earlier, which is equivalent to the equation of, as we see here. And recalling once more of the CIJIFK expression, which we introduced a few slides ago, and recalling that this equals this, okay, which we just showed on the previous slide, little redundancy, just to mention, which implies that this expression equals this. Thus, we have this expression. If we substitute the expression earlier, okay, to this, where we multiplied reciprocal -1, implementing the commutative property of addition gives us, that means we can move the expressions around because of the commutative property of addition, giving us this expression, and recalling the equivalence below of the metric tensor as expressed by the products of differentials. So we recall that. So we bring that back to the front of your mind. The Christoffel symbol can be expressed in terms of the metric tensor of equation A. This is equation A, such that, as we see here, recalling the product rule of expression. So we recall the product rule again of this derivative mentioned earlier. Substituting the product rule expression into equation A, substituting this into this, in other words, gives this expression here. Hence, the geodesic equation can be re-expressed in terms of the metric tensor such that the symmetric metric tensor, or the symmetry in it along each degree of freedom, cancels out of the expression, giving us this. So when you when you cancel out the metric tensors as you see here, without it, we see this expression which gives us the geodesic equation. At this juncture, we are prepared to introduce and derive the Riemann tensor, also referred to as the Ricci tensor, which is expressed as we see here within the Einstein tensor, which we'll elucidate, expressed at the beginning of this video, which once more has a value of the sum shown here, which is the Einstein tensor. So the Riemann tensor, this expression here, is 0 if the manifold is flat. Otherwise, it takes on a non-zero value. So the Riemann tensor is 0 if the metric is flat, and otherwise it takes on a non-zero value, which means curved. So here we have the sense of parallel transport with these vectors, which are going to be mentioned right here on a flat space-time metric. So right now we're going to go into defining this on a flat space before we move on to curved space using differentials, as we shall see in the next slide. Parallel vectors here, these are all parallel vectors in four space displayed in the figure above, which was the previous, where these vectors here are vectors of n-dimensional space in our real numbers. So for us, the n-dimensional is 4. N is 4. So four real numbers are 4 numbers, which is the Minkowski coordinates, a temporal coordinate plus x, y, z. The change in the vectors from VA to VB to VA, as shown in the illustration, is denoted by the difference between the vectors. So we have this difference here, which is a non-zero. We notice a non-zero value. The change in this vector, these two vectors here, is denoted by the difference right here, which is equals a non-zero number. And the change in the vectors VA and VC, you see this is VD and VC, which correspond, so you can actually rewind to the previous video where these vectors are present, the previous slide rather, where you can see these displayed on the figure on the previous slide. I'll just go back, rewind a little bit back if you want to examine those. And so the difference between these vectors here and then the change in the vectors from VD to VB is denoted by the difference as we see here, which all of them equal these differences. This one, and this one. The differences between the two vectors are all not equal to 0, with the equivalent conditions in the change in vectors here. So we see that all of these changes in these vectors are all equal to each other, as we see here. These changes are here. Observe that the difference in the change in vectors are not equal to 0. Okay, that means all of these are not equal to 0. And these are all the changes as we see here, just to make the correlation for the viewer. Thence, between the vectors of here, the changes and the corresponding changes in vectors as we see here are given a sense of parallel transport. The formal definition of parallel transport is the transfer of geometric information along a smooth manifold. The definition of smooth in calculus is the ability for a derivative to exist on a field or region without being undefined or having asymptotes. Now we assemble to the change of vectors here into a commutator. So now these changes in vectors are put into this commutator. As we see here, this is referred to as a commutator, where the commutator adheres to the commutative property of multiplication. Thus, the commutator equals 0, which indicates that the geometry of space is flat. This dynamic is a statement to the workings of the Riemann tensor, which is, as previously stated, 0 if the geometry of space is flat and non-zero if the geometry of space is curved. Therefore, in the case of the Riemann tensor, the changes in vectors, these vectors here, are replaced with the infinitesimal changes of partial derivatives denoted here. So we replace these changes with these two derivatives, delta s and delta t, are upside down delta s and delta t, which vary in the same direction as the rectangular geometric versions, which are these. So we replace these with these, or if you want to say these with these in the commutator, as we'll see in the next slide. The values of the partial derivatives of delta upside down delta s and delta t are given such that, so we see these two derivatives, s and t. Thus, we re-express the commutator in terms of the partial derivatives as we see here. Okay, this is a notation for a commutator, and we see instead of in terms of the delta, the changes in positions, we have it in terms of the differential, the partial derivatives, delta s and delta t, which is flat space, which in flat space will equal 0. So if we apply the field function, and the field function happens to be flat, it equals 0. Distributing the field function across the commutator gives this expression here, where due to symmetry in the expressions along each degree of freedom, we have the equivalent expressions or the equivalent terms such that this along the same degrees of freedom or axis of freedom. Again, the symmetric property. We rearrange the commutators such that, as we see here. Hence, to demonstrate the violation of the commutator, which shows curvature, we once more consider the commutator below of function phi, incorporating function phi, the field function. Thus, we will give an example of a violation of the commutator. We begin with the function b of x, which equals unity as shown below, which means which equals 1. Therefore, we see the value 1 on the second term or the right side of the commutator, which is this side, the right side, and we see the value of 1. And here, if you see nothing, that implies that the value of this coefficient is 1. So we see 1 here. Thus, we substitute the value 1 for b of x, the function b of x that we saw here, into the commutator, which gives us this expression. So we see on the right side b of x. The commutator can be rearranged such that, so we just rearrange it, giving this expression. Implementing the product rule on the right side term, which is this term, gives the expansion of, as we see here. Substituting this into the commutator gives, as we see here, so we see, once more considering that b of x, this function, equals 1. So we went ahead and used this, and we see that this is here. We implemented this on one side of the commutator and substituted it in, which gives us this expression right here. Thus, the commutator can be expressed as we see here. All right, and this is actually the product rule right here. I just wanted to mention that. And therefore, we see this expression here. So moving on, therefore, we once more consider the equivalence of terms due to the symmetric property, as we see here. Thus, the commutator reduces to a non-zero value, as we see here. Okay, because everything is symmetric. After we implemented or substituted the product rule expression here into that, we set this back equal to 1. The coefficients are 1 here, so we can just equivalently express this way. These two cancel out, which leave this term here, and we see that the value of the commutator is this, which is not equal to 0. So here we have a violation of the commutative property, which means it should be equal 0. So we have a non-zero value, which shows curvature. So that's just a little example, commonly distributed amongst many different textbooks and lectures. Thus giving an example of commutator violation, which is the case of curvature in the Riemann tensor, indicates the curvature on a manifold. That was just an example, as I just stated. Thus, the Riemann tensor, consider the expression of the metric tensor previously defined. So this has been quite ubiquitous amongst the tutorial. This expression of the metric tensor, a product of differentials A and B. The metric tensor is denoted, as we see here, and is the product of the metric tensor and the differential commutator, as shown here. Okay, this can be expressed as we see here. Recall the geodesic equation expressed here. So we go back to our geodesic equation, which we defined in the last section for geodesics. Thus, distributing the metric tensor, this, across the commutator of the Riemann tensor gives, as we see here, grouping off the products within the commutator gives this. So we group them off. Thus, the geodesic equation is substituted into the commutator derivative, resulting in the expansion of the Riemann tensor such that, as we see here. So we're just going to go through, we algebraically rearrange the equation according to 5 steps. So here you could pause it and just go through each step. Step 1, we have this, and then we're going ahead and distributing, doing mathematical operations on it. Step 2, we have this expression. Step 3, we go ahead and substitute the geodesic equation, which gives us this. From this steps 2 and 3 up here. So we go ahead and just continue to use mathematical operations on it, and which gives us these expressions as we move. And lastly, step 5, we end up with this expression of the Riemann tensor. And if you go back and pause it, you can actually go back and track every operation and distribution that we did while we implement the geodesic equation on each derivative, right, which we saw before. Okay, therefore, giving the full expression or equation of the Riemann tensor, the full value, which is this right here, this expression or this equation. Okay, remember, you can go back and check out all of the steps. Steps 1 right here. Step 2, or this is step 1, I'm sorry. Step 1, step 2, step 3, pause it. I'll move the cursor out of the way. You can examine that. Moving on to the next slide. The establishment of the Riemann tensor, once more denoted as we see here, allows the derivation of the scalar curvature. Thus, we begin with the previously defined Riemann tensor as shown below. The partial derivative, delta c, is applied to the Riemann tensor as we see here, giving the equation below. Distributing the partial derivative, delta c, across the equation of the Riemann tensor give as shown below. Applying the product rule to the expression gives us, so we apply the product rule to this expression here, gives us this, which reduces to, as we see here, which can be expressed without the brackets such that, as we see here, here we commute and regroup the terms of the expressions as we see here. Using the commutative property of multiplication, we rearrange the partial derivatives, giving the expression such that, as we see here. Recall that the form of this product takes on the value as seen below. Thus, the Riemann tensor, which is a product of the partial derivative and the Riemann tensor, can be expressed as the sum shown here. So all of this reduces to this sum shown here. If you replace all of each term, each one of these terms, this goes with this goes with that, just to be clear. Recall that the terms are symmetric along each degree of freedom or axis, as we see here. As we mentioned earlier, symmetry is integral to the derivation of the equation. Therefore, the right side of the equation can be reduced such that here. So due to symmetry, these two are the same when you add them across, so it's 2 times this expression, which equals that, according to, so you can rewind and take a look at that. Multiplying the reciprocal coefficient of 2 across the equation is expressed such that here, this reduces to this expression, so we have that. Okay, an equivalent expression can be given such that, as we see here, we just, for the purpose of understanding, we just go ahead and or substitute the commutator back into the expression here. So everybody remains familiar with all of these steps. Where R is the scalar constant. So we set this commutator equal to the metric tensor times the scalar constant, which is R. Okay. We eliminate the partial derivative of form C from the equation above, which gives us this. So we remove that from the equation. They simply cancel out because this derivative is on both sides of the equation. Analyzing the equation above conveys that a differential commutator of this must be found that equals the scalar constant. The 4x4 matrix B has a value such that, so we see this matrix here, this 4x4 matrix, where distributing this matrix across the commutator gives an equivalent expression as shown below. All right, so we multiply that and we have this expression here. We set this equal to that, which we give here. If we put this into this, we end up with this expression. Substituting this back into the original equation gives this. So we put this into this, and then we get this, just to make the correlations between the two. Hence, we can conclude that solutions to the 16 components of matrix B give the value of the equation. Hence, we set the equation above equal to this expression of the Riemann tensor, which gives the expression below, as we see here, which once more gives the equation as we see here. For the purposes of a clear explanation, we reapply the partial derivatives to the equation, which gives this expression. Thus, we subtract the right side of the equation, giving as we see here. Distributing the partial derivative of this out of the equation once more gives, we set this all equal to 0. You see these two expressions. Hence, the equation satisfies what is referred to as the Bianchi identity. Thus, once more eliminating partial derivative delta c gives, as we see here, and feel free to look up the Bianchi identity. The equation above constitutes the Einstein tensor, denoted this. Hence, setting this equal, the equation above, this equal to the Einstein tensor, this notation gives the expression of here, which can be expressed as we see here, which is essentially the basic form of the spatial and thus geometric side of the equation that describes space-time as curved by gravity. So this is actually one side of the equation, of Einstein's field equation. Here we introduce the other side of Einstein's field equation, which is referred to as the stress energy tensor. Thus, we begin the mathematical description of the stress energy tensor with the 4 velocity right here, which is the change in position over or divided by the change in time delta t, as we see here. Velocity vector here can be expressed in vector format such that, so we have the 4 vector format here, where we have change in position over change in time, which is a regular law of motion. The interval of time or change in time is set equal to unity as shown here, which means delta t equals 1 unit. Therefore, velocity u can be expressed as shown by the equivalence below. So we see that the partial derivative is the change in the infinitesimally small change in position over time t, which can be expressed as we show here, equivalently expressed as this. Moving on. In reference to the curvature in spacetime, a change in position is an infinitesimal displacement on a spacetime manifold. Therefore, a change in position, delta x, is minimally substituted for a partial derivative on the field function phi in respect to position x as shown below. As I just explained, the change in position is minimally substituted for the infinitesimal change on the spacetime manifold, or on the field function phi, or the curved manifold, which is described by the field function, where the partial derivative on the function delta phi here can be expressed such that, as we already conveyed. Thus, the 4 velocity can be expressed in terms of the infinitesimal displacement as shown below. Okay. Recall that the time interval delta t is set equal to the unity such that here. All right, so the 4 velocity, this actually corresponds with this expression shown below, meaning all of this, just to clarify. Thus, the 4 velocity that here can be expressed as a differential equation such that here, because this is set equal to 1. So here we just, so the term can be, the 4 velocity is expressed as the derivative, being that the delta time t equals 1, which gives this equivalent expression, or 1 unit of time, whatever unit that may be, usually seconds. Therefore, giving the 4 vector expression as we see here. So we have the 4 vector and its components, and in terms of differentials here. At this juncture, we introduce the stress energy tensor expressed below, which we have this, which is, as we see here, made up of the products of 4 vectors here. Here, we see that the stress energy tensor is expressed as a product of components of the 4 velocity vectors, which I just stated, this one, and this one, and where the stress energy tensor can also be expressed in terms of the partial derivatives, as we see here. Thus, we express the stress energy tensor as a 4x4 matrix such that, as we see here, This can alternatively be expressed such that, as we see here in differentials, the component of the momentum tensor constitute various physical attributes of the system. Observe the color-coded highlights of the stress-energy tensor as we see here. The green highlighted components are the momentum density. The yellow highlighted components are the energy flux. The blue highlighted components are the components of pressure. The red highlighted components are the shear stress. The dark yellow components are the momentum flux. And the purple components is the energy density. Thus, the Einstein tensor can be set equal to the stress-energy tensor such that this can alternatively be expressed as we see here. As shown earlier, the Einstein tensor, as we see here, equals 0. This implies that the products of derivatives of the components of the stress-energy tensor, stated here, are equal to the components of the Einstein tensor, which all equal 0, as we see here. There are many methods to solving Einstein's field equations. In fact, Einstein himself thought that the equation was unsolvable until Carl Schwarzschild developed the first recorded solution, which is the Schwarzschild metric. We will not expound on a particular method or solution to the equation here. However, we present an arrangement of the equation that yields solution values to the stress-energy tensor. Once more, consider the equation of, which is the stress-energy tensor in terms of differentials equal to the Einstein tensor, or the value of the Einstein tensor. We algebraically rearrange the equation such that, as we see here, in matrix form, this can be expressed here. So we see this equals this matrix. Therefore, recall the equation of, as we see here, in matrix form, this equation can be as expressed here. So this equals this in matrix form. Therefore, if we have the value of the terms of the Einstein tensor, in other words, or id est, this expression here, which is the value of the Einstein tensor, namely matrices of the Riemann tensor and the metric tensor times the scalar constant divided by 2, one can use the equation above to obtain the values of components, or of the components here, or equivalently the velocity vectors, the products of velocity vectors in terms of differentials, as we see here. This is, of course, a very fundamental and basic method to obtain the value of the stress-energy tensor. Depending on the data available of the gravitational space-time curvature, the equation may need more elaborate and complex solutions and methods to solve them. In conclusion, the cosmological constant lambda describes the expansion of the universe and was later added to the equation by Einstein himself. Thus, with this addition, the equation could be expressed as this, incorporating the cosmological constant. Thank you for watching, and I hope that this video has helped you with your endeavor into the wonderful world of physics. Please like, comment, and subscribe to the Ministry Physics YouTube channel.